Hello.
I haven't made PowerPoint, so recording is fine. But yeah, first of all, I want to thank you, Vanya, and thank your co-hosts in this seminar. It's good. It's really good to see that the field of algebraic geometry is booming so well with all these fascinating talks. I can read the titles and I understand the titles usually, and but it's like another world to me now. But and it's nice, I just want you all to know that I always thought of us, the three of us who were students of Oscar's at the same time, Michael Artin, Heisuke Hironaka, and myself. I mean, we're all three alive, and I think someone used the word legend, which makes me feel as if we're on the verge of kicking the bucket, which perhaps we are. But in any case, it's really it's a beautiful thing to connect. But so then the question is, what should I talk about? Because it's been almost 40 years since I did any algebraic geometry. But the latest thing that I was involved in had to do with rogue waves. I'm a sailor, you may know, and I was contacted by an American who works in Italy, actually in Turin, Al Osborne, who has been using these some soliton equations connected to Jacobians of curves to produce models of how it might work. So it seemed to me I can make a connection, however, with rogue waves and moduli spaces. Actually, John Colorado once said to me when I was a graduate student, the ultimate paper would be shock waves in characteristic P. Now, I don't know, there may be such a paper, but now, by the way, here's a word of caution, Vanya. It says my internet connection is unstable, and
maybe I should ask people to turn off the video, just to make it better.
Yeah, it's best to turn off videos.
I will also
but
turn.
It's my signal is going 20,000 miles into outer space to a satellite in geosynchronous orbit and back again, because I have a dish here in Maine. I have no hard wire connection, but let's see. But I wanted to start by, why didn't this go away? Come on, go away. There, damn, I'll just drag it down there. Okay. So first off, I want to start off my talk by showing you a little video. This will sort of set the tone, right? This is, you can all see that?
There is something out at sea, terrorizing the world shipping.
Out of the darkness came this.
What?
I've never seen a wave as big as this in my whole life.
It can strike out of the blue with devastating consequences.
You hit solid water and it is like running into a brick wall. The entire bridge was wrecked.
Horrific. Monstrous. You feel as if the end of the world has come.
This is the story of a wave that is sinking ships around the world. A killer that defies all scientific understanding. and that no ship is designed to withstand.
Okay. I like that last line, defies all scientific understanding. So that's baloney, of course. And in fact, there's a 200-year-old theory of water waves, which however is still being actively developed. There's lots of unknown things. So, so what I'd like to do, however, is to make a link between. Now let's see if this is a little bit of a juggle with paper and devices, but let's see if it works. Now wait a minute. Why is, oh shoot, what's happened? Why is this not working? Oh, this is crazy. Now I'm putting, wait a minute, let me restore. It says it's mirroring. Okay, good. So why doesn't it mirror?
We still see your notepad, so it should work.
Yeah, I know. I'm putting my hand under it and it's not reflecting, which is, wait a minute, let me just, I know, let's try one more thing. Okay, now. Now it's, okay, good. I came back. Okay. Okay, oh, phew. All right. So, okay, I want to start by recalling some basics. Now it's gone away. Damn, I can see myself in the camera. Jesus. Something's, why isn't, it worked a second ago. Damn. Well,
it's okay. We'll sort this out.
What?
So.
Yeah, I know, but it's no. I don't know what I'm going to do with the rest. I have a few. No, it's just that. Okay, it says it's mirroring here, and yet it doesn't. It doesn't mirror. It's connected here. This must be down here. Here's the software reflector. Oh boy. I think I should probably, this is absolutely insane. Reflector. Your screen sharing, all right, I know
We
that.
see your screen, yeah. We see the
Yeah, I know,
notepad.
but you see, yeah, but you don't see my pen, which is on top of the notepad where I was about to write, which is crazy. I mean, yeah, it's simply not mirroring correctly. Ah, shit. Well, all right, wait a minute. I'm gonna, this is pretty bad. No, not QuickTime. There we go. All right, okay. All right, now I go back to here.
Probably you need to
Screen
connect.
mirroring. Okay, now I have to put 11194. Okay. So now I think it's appearing. It's a little small now. I don't know. Okay, okay. And at least we have a. What? It is okay.
It's okay.
So what I want to say is, say we have two Fuchsian groups here. So I have a disk 1 and a disk 2. It's really delayed hugely. And there's a Fuchsian group, gamma 1 and gamma 2, that give us surfaces of the same genus. Then what's known is, it's extremely slow, it's this connection. So what's known is that there's a quasi-symmetric isomorphism of the boundaries, which commutes with the action of the same fundamental group, okay? So the result is that you can think of the disks like so, and we now do what is called welding. It's like 5 minutes behind what you're seeing. Jesus.
No, just one
Anyway,
second behind. Couple seconds. It's okay.
Yeah, I know. It's not really okay. It's absolutely absurd. Why? It was working perfectly yesterday. I swear to you. This is absolutely lousy. So this is, it's like going in 1 mile an hour trying to connect these two. So the point is, I'm going to talk ahead and not draw as much as just put formulas down. Anyway, it's a marvelous theorem of Bayes that you can then extend the conformal structure to the join of the two. And out of that, you get an entire sphere with the same group gamma acting now as a Kleinian group, a quasi-Fuchsian group. So what happens when you do that is that the join becomes, sure, this is going to work. What? There we go. So this is a typical, these are two genus 2 surfaces. The fundamental group of a genus 2 surface is acting on the entire Gauss sphere here. And on the interior, it gives you a compact surface of genus 2. And on the exterior, it gives you a compact surface of genus 2. So this was the construction of Bayes. And you get these wild fractal curves as they're now the image of the boundary that was welded together. And if you fix one of them, this is a perfectly good model of the Tachmil space, because we have a variable Riemann surface and an isomorphism of its fundamental group, which is then, that pair is then a point of Tachmil space. So in this way, that's the classical theory. Now the point is, what happens if you have a welding, different kinds of weldings? You can, in fact, you can reverse the process, take an arbitrary simple closed curve in the plane, which could be smooth, take the Riemann mapping associated to its interior and to its exterior, including the point at infinity, and what you have is now a welding of the boundary of the unit disk to itself. This is the universal Tachmil space. So let me see if it's worthwhile making a picture. So what you do is, I don't know, let me go back.
David, one option would be to turn off your camera, then it may improve connection on computer. Maybe it will help a bit. Or maybe
turn
not.
off the camera.
But maybe we just keep it. Maybe we just keep it. Yeah.
I think that's just totally, it's not a separate connection, you see. It's going through a single satellite.
Okay, let's just keep it.
Yeah, okay. Yeah, I tried, there's something else called AirPlay. I tried that too. Well, you know, people in their 80s should never use computers. Okay. So now let me tell you how, instead of dealing with the standard moduli space of finite dimension, we go to the universal Tachmil space, which is infinite dimensional. So here, what we have on the side of the Riemann surface
Can I ask
is
a question, David?
Quasi-symmetric. What?
Where, if you take the plane curve, where is the group then? There is no group.
No, there's no group any longer.
Okay.
There's no group. The group disappears. Instead, you have Riemann surfaces with boundary. And when you have Riemann surfaces with boundary, then the boundaries are, the labeling really constitutes the name of all the points on the boundary. So the replacement for the Tachmil space is now a quasi-symmetric map of the circle to the circle. So we're dealing now with the Tachmil space of a unit disk. And if we fix one base unit disk, we have a quasi-symmetric map of its boundary to the boundary of the variable one. Now this is also, we can then glue two unit disks to each other with that homeomorphism, and again we get a plane curve. So what happens, oh yeah, okay, so actually it's on the screen there. All right, right, so the gamma action here disappears, but we still have a map H of the boundary to itself. And when we glue, we again get a plane curve. So let me, if I move this, yeah, I'll just move this now. Oh, that goes away. Okay, so the bottom part is going to appear in a minute. What we have in the case of the universal Tachmil space, on one side, we have a somewhat reasonable homeomorphism of the boundary of the disk to itself, quasi-symmetric. On the other side, we get a simple closed plane curve, well-defined up to translations and scalings. So, so that's what's called T of 1, the Tachmil space with no group gamma at all. So these curves can be perfectly simple curves. They could be ellipses, they can be outlines of ducks, whatever you want. Now I want to shift gears a little bit. So we're now dealing with infinite dimensional spaces, and the bulk of this talk is going to be about metrics on the space of shapes. And to introduce this, I want to read a quote of Riemann. This comes from his Habilitationsschrift. I was totally amazed when my friend Peter Mihor told me about this. And here's the quote. There are, however, manifolds in which the fixing a position requires not a finite number, but an infinite series, or a continuous manifold of determinations of quantity. In other words, the coordinates could be an infinite series of real numbers, or the coordinates might be a function themselves, continuous. So a point is determined by fixing a function, and that gives you a point in the space. Such manifolds are constituted, for example, by possible shapes of a figure in space. In other words, he also anticipated the idea that you could take shapes, analyzing them from the perspective of differential geometry, and make some sort of a moduli space out of these. Now, yeah, so now 10 minutes later, you have my notes are appearing on the screen. Okay, but I would like to mention that the first real oh, I see. I'm actually on the next page from this. That's just got T of 1, the Tachmil space. The first result actually was this spectacular Theorem of Arnold in 1966, in which he considered diffeomorphisms of a space of any dimension which preserve volume. And he put the simplest possible Riemannian metric on this. The tangent space to a group of diffeomorphisms are smooth vector fields. And the simplest way, let's assume we have a compact base or it goes to 0 to infinity, we put an L2 norm. We just, okay, here's the part I'm actually talking about. Arnold's result is in the middle there. So you put an L2 metric, that's there on the screen on the left, on the vector fields. And what he discovered is that the equation for geodesics in this metric is exactly, I don't know why, I'm not moving it. What? There's a mind of its own. Is Euler's equation for fluid motion. So this is incompressible fluids without any viscosity. And there's Euler's equation is written down there in terms of the velocity vector field and the pressure. But integrating this, you get a one-parameter group of diffeomorphisms, and these are exactly geodesics for this metric. Okay, so I got very interested in this. I should mention I collaborated for last 15, almost 20 years now with Peter Michor, a differential geometry in Vienna. And in fact, most recently we wrote a paper we called the Chow manifolds of differential geometry. So in this paper, we fix an ambient manifold, compact, say, and look at all its submanifolds of some topological type. And then the totality of these is itself a shape space. It's an infinite dimensional space. And there's a huge variety of metrics which you can put on this space. So, so we've been studying this. Now, an important point about metrics on infinite dimensional spaces, after all, they are nonlinear versions of Hilbert spaces. If you have a quadratic metric. So if you know any PDEs, you realize that everything that is connected to PDEs is is governed by how smooth the functions are. And we have this ladder of sub-F complexity. So continuing to reflector 3. Oh, Jesus. Done. And now I've lost my pad even. Well, maybe for a while, anyway, I don't need the pad. Sorry, what a useless thing this.
You see some
This
part
was.
of the.
Okay, so anyway, so naturally, what happened was that we decided to look. I decided to look first. What happens if you drop incompressibility? Why don't we take an L2 metric? So the simplest thing is as you see from Riemann's talk, actually, was to take the set of simple closed curves in the plane. This is in some way the simple example. It's sort of like looking at elliptic curves. The totality of simple closed curves in the plane. And they can be smooth or not smooth, but let's assume that we include smooth ones anyway. Now, what's the tangent space? So an infinitesimal deformation of a plane curve is simply given by a normal vector field along the curve. So an infinitesimal motion pushes every point. We're not interested in going tangential to the curve. It's only the normal part moves the curve. So a normal vector field along the curve is the tangent space. So, okay, you can take arc length parameterization of the curve and make an L2 metric. So I was sitting here in my study, actually, some 20 odd years ago. I thought, well, let's see how this works out in MATLAB. And everything was going screwy. It was just going bananas. I was getting terrible results. And I was totally puzzled by this until I then began to sort of think, well, wait a minute. Why am I getting zigzaggy curves? Maybe there's something about zigzaggy curves. And you see, here's the secret of a zigzaggy curve. If you have a very sharp zig in a curve, if you push it sideways a tiny bit, the tip of the zig shoots ahead very fast. So the point was that, in fact, it was possible to create paths of arbitrarily small length between any two plane curves. So here's an example. I hope this comes up anyway. Okay. So what's happening here? A perfectly good geodesic, no matter what your metric is going to be the family of plane curves just getting bigger and bigger and bigger. So that's a one-dimensional family of plane curves. But here, what's happened is the curve has been perturbed a little bit to have wiggles in it, and then the perturbation it phases in and then it phases out again. Turns out that under the picture that you see, the distance between the final simple circle and the initial circle has shrunk by a factor of about 1.9. And if you make the zigs and zags sharper and sharper, you can make them arbitrarily close. So this is a very interesting thing, which wouldn't happen in finite dimensions. What's happening here is what are called in differential geometry the conjugate points. So the conjugate points, if you have a geodesic and you set out in an infinitesimally close geodesic, it can diverge from the given geodesic, or it can come back and cross the initial geodesic. And if it does so, the place where it crosses is called a conjugate point. So what's happening in this interesting metric, it's true that the global distance collapses, but what's happening is that the conjugate points are dense on every geodesic. So what we gradually found, Peter and I, investigating this, is that everything has to do with the sub-F weight of the metric. So what you can do, so typically sub-F weight 1 would mean that you square derivatives of the function and integrate those, and you put those into the metric. So I could look at the the function which parameterizes the plane curve, and I don't just I can look not at its values, but its first derivatives, or its second derivatives, or its third derivatives, and square those and integrate them over the base curve which you're using as your parameter space, and get stronger and stronger metrics. So these are more, they're much tighter metrics, and they force curves to be much smoother, geodesics to be much smoother. And in fact, it's a hierarchy. It isn't just integers, it's any real number, because the best way to imagine the Sobolev hierarchy is by taking Fourier transform. And then it's a question of putting in, if it's a function on a circle, so it's a Fourier series, A sub n, you put in a factor, absolute value of n, to various powers, and make their metrics with that extra factor of a power of n. So if you have first derivatives in it, it puts a factor of n squared into the metric. If you put a single n in there, that's the h1/2 metric. And if you put, instead of putting n in there, you put 1/n, you get the h-1/2 metric. So there's a whole marvelous hierarchy of metrics of different strengths. So this is what Peter and I have been playing with now. Right, so I've shown you how Sobolev weight 0 does sort of weird things. Sobolev weight 1 is a wonderful thing. If you put a metric, on plane curves which integrates the derivative of the parameterizing function, but it doesn't integrate the function at all. So you're dividing out by translations, basically. It then turns out that there is what's called a Riemannian submersion from a Grassmannian. Can you hear me, or is I hope my voice is coming?
Yes, we can hear you perfectly.
Are you guys hearing me?
Yes, yes.
Oh, good. That's what counts. Okay. Well, it turns out that there is a map of a Grassmannian of a Hilbert space. It's not a finite dimensional Grassmannian. The Grassmannian of a Hilbert space, it's another infinite dimensional thing, but it has very nice geometry, just as you might expect. There is a submersion means it's a map of a one Riemannian manifold to another with the property that the metric on the space downstairs is always isomorphic to the metric upstairs on the parts of the tangent space perpendicular to the fibers of the map. So we have a map from here to here, and we have fibers of this map, and we take in the tangent space the perpendicular to those fibers, restrict the metric to that. That should give you the metric on the base space. It turns out that this H1 metric is a submersive quotient of a Grassmannian. The result is, so here's a beautiful picture of a closed geodesic. And it doesn't just go through simple closed curves. It goes through immersions, and 4 times it actually goes through places where the immersion also instantaneously collapses. So where's my, can't find my, oh, there it is. So I don't know if you can see my cursor, but it's on the top left, it's a circle. And moving to the right is the geodesic. It crosses itself. So now it's going inside out. It's gone inside out. At this point on the right, it's got 2 singularities, which then smooth out, and it's now turned inside out. Then it decides to do even more tricks. it crosses itself again, becomes singular here, expands, and now that this part in the middle is right side, and it's inside out on these 4 loops, and then it retraces its steps with 90-degree turn, and finally along the bottom row, it gets back to the circle again. So, so this turned out to be an incredibly beautiful picture, and it's so simple to calculate with because of this connection to the Grassmannian. Okay, but then how about the universal Tachmil space that we started with? You see, it turns out that there is a very well-known metric on the Tachmil space called the Weil-Petersen metric. Very beautiful metric, and it was a source of considerable conjecture and mystery until this amazing pair, Tachmil and Theo, got into the act. I just want to mention, because this is such an international Zoom meeting, Tachmil is actually an Armenian who got his mathematical training in Moscow, but he went to Princeton Institute for Advanced Study, or maybe he went to Feinhall, I don't know which. But meanwhile, Theo, who comes from Malaysia, and I'm not sure where he got it, I think he got his degree maybe in Kuala Lumpur, but anyway, they meet up in the US and they work out the whole theory of this, the Weil-Petersen metric. It's a spectacular theory. Parts of this were known before them, but it was only their work that they realized that actually the standard Tachmil space is fibered it has by subspaces, still infinite dimensional, which are themselves sort of cosets of each other. Each of them is a complete metric space for the Weil-Petersen metric. And the basic one, which contains smooth curves, very recently it's been discovered that the curves in this Weil-Petersen Tachmil space, universal Tachmil space, are exactly the ones whose arc length parameterization is 3/2 Sobolev. So it's and in fact the metric is a 3/2 metric. It comes from a norm which in Fourier series is like absolute value of n cubed minus absolute value of n. That's the so because it's n cubed and because it's the Fourier coefficient squared, it means that Sobolev weight is 3/2. And this is an absolutely fascinating space. Geometrically, you see, each space has different characters. The previous one, Sobolev 1, was still positive. By the way, it was all positive curvature. I forgot to mention that. But the conjugate points are definitely discrete now. But 3/2, now the curvature is turned negative. It's always negative, but in high frequencies, it's almost flat. In other words, what turns out to be the case is the so-called Ricci curvature is finite. So you have to realize in an infinite dimensional space, if you take Ricci curvature, you're making an infinite sum. What you're doing is, in this interdimensional space, is you're looking at planes like so. You're fixing one of them, say this one is fixed, and then you're letting the other one vary over an orthonormal basis of the complement to the fixed one, and summing the sectional curvatures over all of those complements. So in an infinite dimensional space, for the Ricci curvature to be finite, means that the curvatures go to zero very fast in high frequencies, so long as simply one of the two directions is a high frequency direction. It's going to be finite. It's got to be very small in order to be finite. In fact, it's a Kähler-Einstein metric, which is I mean, it has everything for it. it's homogeneous. All its sectional curvatures are negative. It has unique geodesics joining any 2 points, and it's almost flat. So it's a lovely space. So now to go, if you go higher, then Peter also has a team working with him. So there's a whole bunch of students, Martin Braveris and Philip Harms, and who have been developing his theory. So they've extensively worked on the higher dimensional subleft norms. It turns out as soon as the subleft norm is at least 3, they now can prove a global existence theorem for geodesics. The curvature is mixed. It's not all negative. It has some positive directions, some negative directions. And I think that somehow understanding the negative directions as well as the positive directions, separating them out in some intuitive ways, would be a great advance. And they conjecture, actually, as soon as the subleft weight is at least 2, that this is going to take place. Okay, so now I've even lost not only that. I'm so disorganized. Wait a minute. Yeah, I've even lost. I can't believe it. Fiasco. It was always so simple, standing at a lectern and giving. Oh, wait a minute, right here underneath the computer. No, okay, right. So you've seen this one too. Right. Okay, now, oh, geez, I really do need at this point to draw to get some formulas. How can I do this without showing formulas? Damnation. Let me try. Is it still working or not? I've got to show you some formulas. That's the problem. So what I want to do is to get to waterways at this point.
David, one option, if you stop sharing the screen and you can write down the formulas and show it in the camera.
Oh, I see. Oh, I just show it in the, I show it in the camera.
We can try.
Right.
We can
okay,
try.
Right. Of course. Right. So how do I do that?
I think you need.
Right, of course.
Maybe you need to stop sharing the screen.
A little bit weird.
Or maybe.
I see. I've got to reverse my camera. So yeah, but this is a MacBook Air. It's not like an iPhone.
Wait.
I've got to turn the camera around.
David, first you need to stop the sharing the screen, because now we see your screen. Yeah.
Oh, no, but you see, I could do this. What if I do this?
Okay, we probably can do this. Yeah. I think it's actually okay.
I don't know if that's visible.
Yeah. Your internet is actually, connection is very low. But we can see it, yeah. Yeah, it shows, yeah.
Okay, wait a minute. I've got to say the word, okay. So let me say the words first, and then I'll show you the formula, okay? Okay, so we're talking about the waves on the surface of water, which Feynman has a marvelous quote here. He said this: water waves that are easily seen by everyone and which are usually used as an example of waves in elementary courses are the worst possible example. They have all the complications that waves can have. That's Feynman's quote. Okay, so in any case, it goes back, there was Stokes in the 19th century, who was a big developer of the theory. But there's a basic case. First of all, I have to say, that I hope you know, well, I assume you know fluid mechanics. So, so if you have the velocity of the water, it has a div and a curl. The div being 0 means that it's not compressible. The curl being 0 means that it has no vorticity. So vorticity is, of course, the spinning of the water. Now, what is one of the most simplest theorems in fluid mechanics is the fact that vorticity is constant when it is transported along the flow of the water itself. So, so what that means is that in the wide open ocean, if you have a calm day with no winds and everything settles down, the water, the motion stops. At that point, the vorticity is 0. If now a wind arises and it begins to have waves and motion, what tends to happen is that it gets a little bit of vorticity on the surface, but down below, the vorticity, the surface water doesn't actually penetrate down very far. It stays on the surface. So the vorticity below remains 0. And for that reason, you can study water waves to a certain extent by assuming that they're not merely incompressible, but have no vorticity. Now, when both the div and the curl are 0, you have a harmonic, it's a harmonic flow. And so the classical approach to studying water was to take the, well, so I have the formulas, well, anyway, the formulas just say that the div and the curl are 0, which means that the velocity is going to be the gradient of a potential which is harmonic, a harmonic function and defined throughout the bulk of the water, going to 0 at large depths. Now, another Russian, Zakharov, did this pioneering work in, I think, 1968, in which he realized that under the assumption of no vorticity as well as incompressibility and no not viscous, that there was a Hamiltonian that controlled this. And so he made a Hamiltonian out of 2 terms. One was the kinetic energy of the water, the integral of the velocity squared over the totality of the water. If you do this in the standard way, you have to assume, of course, that the water is still outside some compact region, so it goes to 0. And then you have a potential energy, which essentially is from gravity. So it's gravity is the external forcing field, a potential field. And so that you put potential energy in there and you add the 2. And he showed that the equations that go back to Stokes and all for the motion of the water was a Hamiltonian flow for these for this Hamiltonian. Now, an even nicer situation is to cut down the dimension. If you assume that the water waves are just a linear progression of waves in one direction, so there's only one horizontal direction, and of course you have a vertical direction underneath the water, that means that the potential is a harmonic function in 2 dimensions, which is time varying, which means it's the real or the imaginary part of a complex analytic function. So now you can take, you can take Riemann mapping theorem and map the water itself. It's actually a vertical slice of the water going down to the bottom or to minus infinity if the water had infinite depth. And you generally, you either, some people assume it's periodic and then it wraps around. In any case, you make a Riemann mapping to the unit disk. and so you put your whole problem as a problem that looks as if complex analysis should solve it. Well, it turns out it isn't quite as nice as that. When they do so Zakharov got a younger collaborator, Dirichlet, who is they have published many papers together, and Dirichlet individually. I think Zakharov is maybe not quite as old as me, but is getting on. So they have then investigated this. Now, the first thing I want to, I'm going to try to put a formula here. Now, oh God. Okay, wait a minute. Now, if I put my finger.
Yeah. David, do you still need demonstration of your screen? If not, we can just switch it off. David.
Well, I wanted to show these formulas.
Yeah, but
so these. So what?
Maybe we first turn demonstration of your screen. There's a button on computer. Stop sharing the screen. Then we can see. Maybe it will be better.
All right.
You're not using it anyway.
All right. What?
Or you plan to use it?
No.
Later.
What you want?
Maybe
well, I don't have. No, I don't have to. I can actually say all of this out loud. It's just that there's a little formula which is interesting. I'll just say it out loud and see if it works.
David, we can see it. If you put it on the screen, we'll see it. We'll see it. If you put it on the close to the camera, we'll see it. Yeah.
Where my finger is, where's my finger? So that's the kinetic energy. The velocity, that's the grad of the potential integrated over the bulk of the water, which is the total kinetic energy of the water. Now the point is, however, that you rewrite that, it's the divergence of the potential times the gradient of the potential, simply because of the fact that that the function is harmonic. And then by Green's theorem, it's an integral over the surface of the water of the potential times the normal derivative of the potential. So the potential is a harmonic function, and it can be it can be solved for as a Neumann problem or a Dirichlet problem. So if you know the potential on the surface of the water, you have a Dirichlet problem, gives you the potential back. Or if you have the normal derivative, you have the Neumann problem, you also get everything back. Now, the energy is now this product. So now, what does that mean for shape space? We think of the surface of the water as being a shape, and we want to know what kind of a metric we have on the shape. Well, we have to use the kinetic energy of the water. But so first of all, the derivative of the shape, the normal derivative of the potential was the velocity, the normal component of the velocity of the surface. So that's the motion of the surface. The velocity, the water is moving, so its normal component on the surface is the motion of the surface itself. So that's the partial in the normal direction is precisely the vector to shape space. But what we need to do is to multiply it by phi itself, by the potential. Where are we here? Yeah, right, here we are. It's my finger. There we are. Right. So what's happening is you have to take the solution of the Neumann problem, solve the Neumann problem, and then take the boundary value. So that people call this the Dirichlet-Neumann kernel, getting one from the other. So it means that the metric is precisely the integral of the velocity field with that kernel. So it's an integral metric, not a derivative at all. Now this kernel, it's only very slightly singular. It has log singularities along the diagonal, and so essentially that kernel is smooth things rather than making them rougher by differentiating them. It's a smoothing kernel. So what this means is that the metric is Sobolev minus 1/2, which is really weird. It's a completely new situation. Oh, by the way, I see. So to kind of complete this, so this is from this paper of Zakharov and Dyachenko, in which they use this complex method to solve the water equations with given initial conditions. And as had been discovered some time ago, they're unstable. So in this case, I think that in this the time is this is after time equals 80. So they started at time equals 0 with a very regular train of waves, but they perturbed it infinitesimally. And this is what happened after 80 units of time in their computer. Bingo, they developed rogue waves. So rather than being beyond the realm of science, there is a wonderful theory. And what I'm hoping is that that our group too can make contributions. I don't think anybody ever anticipated that negative Sobolev weights could conceivably be well defined. The geodesics. I mean, well, it's not the geodesics because there is a potential term. But okay, so first of all, it's been regularized by, it's an incompressible flow, which simplifies things. And secondly, it has that gravity potential in it. But there are some preliminary results saying that it's a well-posed problem locally, but just a few. It's by no means. They certainly do seem to meet singularities in finite time, and the theorems are weak still. So anyway, that's the story, and I think I certainly hope that that rogue waves will be a beautiful chapter in applied mathematics in the next generation or so. Okay, so thank you for listening, and I'm sorry this fiasco of I don't know what the hell went wrong. I mean, at least I didn't buy reflector.
David, thank you very much, and I think it was okay. Let's thank David, everyone. With yeah, thank you. There's option of thank you. Okay. Thank you. Yeah. We actually have a lot of participants, like more than 300 people. And David, do you mind if we slowly move to question and answer session?
No, that's fine. You prepared me for that. And
yeah. Is it okay if you stop sharing the screen? I don't know how to do it from my side. If you click the button, there's some button in the Zoom. Maybe I can do it, but I'm.
Wait a minute. Hold on here.
If you just go to Zoom.
Oh, I know what's happening. I've got to. Oh, I got to move it. I see what's happened. Yeah, I've got it. Okay, so now stop sharing. No,
the Zoom screen.
Back to meeting. Yeah, I know. I'm first. I have a screen now with. Oh, here we go. No share. No, I want to not share. You sure I'm still sharing?
You're still sharing.
Oh,
see
here we
your
go. Stop
screen.
share. Oh, no, done. Now it's gone, I think. Right?
No, we still see your
I
screen.
think it's gone.
Maybe let me try to do this. I just don't know.
Manya, the screen at the top is saying you are viewing Piotr Pragac's screen. You could just forbid anybody else from sharing.
Ah, yes, Miles. Thank you very much. Okay, give me 1 second. I think I did this.
I'm not sharing my screen according to this.
Wait.
I'm looking at Piotr's screen. It says.
Okay, I did this, but it doesn't work. So I still see.
But it's not my screen, I don't think, is it?
Ah, okay, let me do this. I'll share my screen. And then I click it. So wait.
It says it's Piotr Pragac's screen.
Yeah, okay. Now it's good. Okay, I did it. So sorry.
Janos.
Okay.
Miles. So many old friends.
Yeah, now we can see everyone. Okay, David, I have people send me a lot of questions. Do you mind if I just go one by one?
No, that's fine. That's fine.
Okay, so first question is from Jesus Martinez Garcia from Essex. He asked, can you comment on what moved you to take a radical change on your research discipline and which difficulties you encountered when moving to a new field? And did you regret about it at some point?
Yeah, well, I said, no, I never regretted about it. I mean, I had always had various interests beyond mathematics. I mean, when I was an undergraduate, at the time, I studied quite a lot of neuroscience, and which was a very primitive field at that point. I mean, people really don't realize how much has happened in those 60 years. So anyway, no, I never regretted it. And I had also, as a high school student, had loved computers and made a computer out of World War II surplus relays, which worked fine until a spark lit up its paper tape and the whole thing burned. So that was the end of that computer. I think I still have problems. So no, I don't have no regrets. I spent a lot of time reading more computer science, reading
Ale, ti posso
more about
chiedere un po' di
neuroscience.
silenzio, per favore? Grazie.
Sorry, what?
No. It's
yes.
I think it was some noise. So sorry for interruption. Yeah.
Oh, okay, that's all right. All right. There was a guy named David Marr who had just recently died, who had written a book which is very inspiring, and made it seem as though artificial intelligence of some kind could move forward if one stuck to the case of vision, and that indeed turned out to be the case. So no, it's not so simple. I mean, I would say that applied math in general is a much less organized area than pure math, and people tend to be all going in different directions. So, but you know, I made some close allies and began to get into the new field. It was fun.
Thank you.
Okay.
David, another question from Misha Zeidenberg from Grenoble. He asked, what in your opinion is most remarkable of Zariski personality?
He was a very intense person. I mean, when I was an undergraduate, I was, of course, very much in awe of him. Several times I've written that it seemed like he was in a, he had a secret garden. When he said the words algebraic variety, it made you think there was some marvelous universe of ideas and things that lived somehow, and that he was in touch with. So then later on, as he got older, Mike and I used to have lunch with him once a week, and and there was this wonderful autobiography that my friend Carol Parikh wrote based on his the notes that he'd given and his life. I mean, he never liked to talk about his origins and so on, but what was wonderful about him was he really welcomed new ideas into algebraic geometry. He was diametrically opposite from Andre Weil, who really didn't like Grothendieck at all and thought that this was craziness. He refused to acknowledge that Grothendieck's ideas were absolutely the right ones. Zariski welcomed him. Grothendieck came twice for a semester to visit Harvard. So no, but yeah, so he became a good friend, and Yoli, his wife, was fabulous too, in taking care of him, and yeah. Anyway,
thank you, David. The next question from Koshar Birkar from Cambridge. He asked two questions. First is, what are some fundamental differences of doing mathematics now comparing to 60s and 70s?
Oh, well, it's night and day. I mean, in the 60s, pure math was a small field. I remember Barry Mazur was a good friend of mine when he was an undergraduate at MIT, and then he went for a while to Princeton, but then he came back. So we used to say, you know, we don't want to specialize. We want to learn all of mathematics. We want to know what's going on. I mean, it's not that big a field after all. Why can't we get a good sense of? And it didn't seem impossible in the 60s. I mean, it was, but you know, it's probably 10 times larger now, and sadly it's much more specialized, and in each specialty, there's infinitely many technical definitions which you have to master before you can get to first base. So yeah. So actually, you know, you sent me these questions because so there's also the question from Eduardo, which sort of connects to this in a way, about, it's quite true that for a while I was all fired up about the idea that art and mathematics had pursued parallel paths from roughly from 1800 through 1970 or something like that. I particularly liked the parallel between von Neumann and what was it? His two collaborators. Anyway, inventing the idea of Monte Carlo algorithms to simulate the explosion of an atomic device, being so similar to abstract art, and especially splatter paintings. But I think as far as that point of view is gone, there's another huge thing that has happened where I think art and mathematics have diverged. And that is that unfortunately, the art community has been bought. It is now a playchild of billionaires who entertain themselves by going to auctions and spending $100 million on a piece of canvas, and then hoping to sell it for a couple of $1 million more in a few years. So the whole art market has has become corrupted by presence of money, whereas pure math especially toils along in blissful poverty. At one point, Jean-Pierre Serre had a marvelous quote, and he said, "The reason the International Mathematical Union is so successful is that A, no one ever becomes president who wants to be, and B, it has no money," which is not entirely true now, but it still is essentially has no money compared to other organizations. So anyway, fortunately, that's something to, it worried me tremendously when I discovered that the American Math Society had built up a kitty of $100 million. That struck me as seriously dangerous. But yeah, the other part of Kosher, your question, Kosher Burkar, because I have these questions in front of me, you see, that Vanya sent me yesterday, comparing pure maths with applied maths. Of course, they split because applied maths fall in love with computers. I used to look over Garrett Burkhoff's shoulders and see this Fortran code, and there on the page it said, x equals x plus 1. I thought, this is crazy math. X equals x plus 1. I didn't realize that the x on the left means the new value of x, and the x on the right is the old value of x. But in any case, they fell in love with computers, obviously. And but it's a very disorganized field, applied math. Everyone's doing their own thing. Just, I mean, there's even less cohesiveness than in pure maths. And in pure maths, you have instances where people do come together, and you know, topological ideas are introduced into fluid mechanics, and of course, string theory has been a boon for insanely complex mathematics that brings together all sorts of fields. So, but applied math, unfortunately, really is thoroughly split, so that you know, people simply do not talk to each other. That's an unfortunate situation. Okay.
Yes, thank you. And the next question is from John Autumn from Oslo. It's about pathologies. One aspect of your research, which we all found particularly inspiring, is many construction of exotic or pathological examples. It would be interesting to hear your thoughts on constructing such examples, perhaps how some of them came about. For example, quartic double solids, Artin Mumford example.
Well, yeah, the quartic double solid came about because Mike and I were talking about you know, the issue of unirational versus rational, and the idea of torsion in H3, isn't it? Came up, and I think but he had been studying these elliptic bundles in connection with his interest in the Brouwer group and all. And so I said, can't we, that seems like the way to really look, to look at various conic bundles and see if we can find anything. And I don't know, I've forgotten specifically the quartic double solid, how that came up, but I mean, that we basically brainstormed about different ways to come up with interesting examples. But I have to say in general that maybe my favorite one was this p-adic surface of general type, which defined by lifting a marvelous combinatorial object from characteristic P into the p-adics. So it had this beautiful uniformization, and I mean, I think I got a greater thrill in a way from crazy counterexamples almost than theorems, because I mean, it's like having a gem in your hands, and and it allowed me, moreover, to quote Lewis Carroll in the pages of the American Journal of Mathematics, which I was pleased to be able to get away with. Anyway, yeah, I don't know. For me, I guess examples are the way to really understand math better. That I'm absolute opposite of Grotnik, who understood things most clearly by having a completely abstract way of describing them. And not that I then once I have the examples, if I can build up to the abstraction, then so I mean, to understand schemes, I mean, I had to understand the 0-point schemes better and nilpotent rings, and then everything began to fit together. Yeah, I mean, so I mean, the whole idea of the ideals with which had primary components and had so the corresponding scheme had nilpotents. That was I don't know. It really. I mean, the whole idea. Yeah, a twisted cubic curve collapsing into a plane cubic with a double point plus a little nilpotent at the double point was. I mean, to me, that's the whole story. That if you understand that, you understand schemes, right? It's anyway. That's how I feel.
Good.
Okay.
Thank you. Another question from June Park from Pahang. He asked about what was Igor Shafarevich and Kunihiko Kadaira as mathematicians and as persons.
Well, I met Igor at the same time that I met Yuri Manin at the International Congress in Stockholm, where it was early enough on that this whole blockade and all those who could travel and those who couldn't wasn't so bad, and it was just. I mean, Shafarevich was so impressive. I mean, I don't know, like Zariski, I mean, his intensity, as I was going to say, if I ever get to Moscow to give that talk in his honor in your memorial series, I mean, he's sort of a bear of a man. I mean, he looks like a Siberian bear, a big man, and you just believed what he said, and I was very upset, by the way, when he was accused of anti-Semitism, which I have a blog. I don't know if everyone listening realizes that I have a blog on my website, and I have a whole post about Shafarevich and the incident when the some people tried to kick him out of the National Academy for anti-Semitism. But in any case, I quote at length his letter to me at the time. But he was so passionate, and he was passionate about Russia, obviously, and passionate about the history of Russia, and passionate about the traditions of Russia. So in his presence, you couldn't doubt that these were important things. So I just regret so much that I only saw him once more when there was that Steklov anniversary meeting. Wait a minute, or did I see him twice? Maybe there were two times I saw him later. But
in 1966
one time
ICM.
Yeah, Miles said it was twice.
No,
I see him
there. I didn't go to the ICM. in '66. So no, I wasn't there. No, but at one point, you know, I had this email from him saying it was before, I forget, maybe this was the Steklov meeting, the anniversary of Steklov. Anyway, that an associate of Solzhenitsyn could meet me and give me a group of homeopathic drugs to take to Solzhenitsyn's, to take to Sakharov's wife, I think it was, or was it Sakharov himself, or I think his wife, as I vaguely remember. And at that time, of course, the American customs was bananas over drugs. And I thought, having in my suitcase a box which I haven't even opened, and there, in fact, going through customs, there it was, all of these bottles lined up. Well, going into the Soviet Union, there was nobody batted an eyelash to my bringing bottles with unknown contents into the Soviet Union. They instead confiscated Time magazine. So anyway, I delivered these homeopathic medicines for him. No, but I found it, and I found his lecture in Göttingen very attractive. I thought it was a very inspiring lecture. Kodara, I never really got to know. He was a very shy person, and although I met him, it was very hard to draw him out, and I really didn't have a sense of the man. I mean, he was so shy, and he just like would say, you know, oh, I've done nothing, you know, and no, I'm not working on anything. And it was, yeah, very strange that, but that was the nature of the man. Okay.
Thank you, David. One question
neural
from
nets.
Yes, about neural nets, and basically we can maybe summarize to what extent you view artificial intelligence as a field that motivate mathematics similar to what physics done previously.
Yeah. No, yeah, I'm sure you're all aware that the last 10 years have been an unbelievable boom for artificial intelligence. Actually, it's not the first time. In my own lifetime, it's had two previous booms when everyone was enthusiastic and thought that, you know, real robots were just around the corner and what was going to happen. And the first two booms fizzled utterly. But I have to say, it's my personal opinion that the present boom is not going to fizzle, and that very unfortunately, it's also not going to be in the least bit like what's happening in physics. I mean, the difficulty is similar to the difficulty in neuroscience. So neuroscience had a big push in the back in the 50s, maybe 40s, 50s, 60s, when people realized that they could make recordings in monkey visual cortex and correlate those with the stimulus that monkeys were seeing, and that they could ascribe to neurons a clear computational role. However, what happened subsequently is working further into the brain. There were only just a handful of areas in the brain where any tight correlation between neural activity could be connected to something that the monkey, or sometimes they're with cats, or also to some extent with human beings, because some people being treated for epilepsy, it's essential to localize the, sometimes the only treatment is to operate, to remove part of their cortex. But you need to localize as tightly as possible the place where the seizure originates. So they expose the skull, and with the person being fully conscious, they can stimulate the cortex. So there's many parts of the cortex which seem to have sort of really random associations with peculiar things, and nothing very specific, nothing logical. So no in what's called inferior temporal lobe, which is connected to shape, there's no nice correlation between what neurons are doing and the way we think of which shapes are similar and which aren't, and there's a whole confusion. They seem to respond to colors, to textures, to the shape themselves, to motion. I mean, it's all mixed up. Now, unfortunately, what's happened with AI is that it has pursued exactly that route of no longer using explicit representations. So one of the big breakthroughs in my book is what's called word to vec, word, then the number 2, and then VEC, vector. And the idea of that was to use the lexicon in a language and associate to each word a point, let's say, in a 100-dimensional space. And you train this association to these points. And you train it from a whole lot of, exposing it to a whole lot of data. So for instance, one thing you get is you look for a word which in this 100-dimensional space is close to king and is close to woman, but is far from man. And bingo, you find the word queen. I mean, it's an extraordinary tool, and it's used now in all these natural language programs. And it's even been shown that that this huge 100-dimensional space is learning grammar, believe it or not. It turns out there's a fantastic piece of work in which it shows that an intermediate dimensional projection of it onto merely, let's say, a 20-dimensional space, when you take the right 20-dimensional space, you find the parse tree of the sentence laid out for you. I mean, but what's happening in all of this AI stuff is that it's all done by training, and there's no explicit representation. It's moving in the direction of imitating the brain, but being essentially unreadable and uninterpretable by human beings, which is a sad but true fact about deep learning. And this may mean that we do eventually, maybe even relatively soon, like 20 years, 50 years anyway, create robots that, but we won't really know why they come to some conclusion and why they don't. I mean, they may be as ignorant of what's going on in their heads as we are about the firings of our own neurons. So anyway, that's, no, I was going to talk about this in Moscow, and so I've, with the help of a couple of my students, I've read pretty extensively on that, and it's discouraging. Okay?
Okay, thank you. And the next question about what are your most favorite piece of research work so far?
Oh my God. Yeah. Well, you know, one piece of work which I just was convinced that it should open up a whole new set of tools was that paper back in the 60s about abelian varieties and how these finite Heisenberg groups dominate the commutative algebra of these rings, of their projective rings. And I don't know, I just thought that this, and how then you can even define a kind of a two-adic theta function, which coming from an abelian variety has a Gaussian property. Anyway, that was no one ever took that up as far as I know. But okay, what most recently there was this lovely paper where which I wrote with Vasilis Gidis at Brown, in which there's a whole lot of work which shows that natural images of the world seem to have roughly scale invariant statistics. If you blow them up, they have the same statistics as the big picture that you're looking at. I mean, of course, you have to allow for the fact that sky is on top and stuff like that. But if you're in a forest, say, and you take big picture or a small picture, the statistics are pretty much scale invariant. And so the paper, anyway, one of the main points was that if you have a model of a scale invariant images, it is not represented by measurable functions. What your eye receives cannot be modeled as a measurable function. It has to be modeled by a distribution of Sobolev weight minus epsilon. So for any small positive epsilon. That was a fun thing to stumble on. But you know, recently I got so excited by questions in history of math. I mean, most recently I've been corresponding with a couple of people. There's this fascinating question about whether or not the Chinese knew how big the world was before the Jesuits came. I think it's an unsolved question. There's a lot of indirect evidence that the Chinese did know not only that the world was round, but that they knew its actual dimension. But absolutely nothing was written in anything that survives to this day. I mean, so I get seduced by things like that, questions like that. So I've written a couple of papers connected to that that I think are a lot of fun. One of them came out of the shape work. It showed how you could take an 11th century map of China and warp it onto a contemporary map using the ideas from shape theory. And you can then see from that how I feel it reveals what they were ignoring and what they in order to sort of force the Earth to be flat. They were definitely ignoring some data, which I'm sure they had at their disposal. But yeah. Anyway, so yeah. Okay, I don't know if you have other questions. This is what
people sent me more today, and also there's some questions in the chat. So another question is, what kind of differences of atmosphere for doing research you felt during your change of topics?
Oh, well, the atmosphere is totally different. Yeah, I mean, for one thing, all the graduate students I had in computer vision, I had roughly the same number, maybe a few less in computer vision than I had in algebraic geometry. But they all did computer work. And they all worked with real data, maybe with one exception, Yang Wang. But when I first started, I had two people who signed on as graduate students with me. One of them had done very strong work in mathematics, but wanted to really do beautiful work in computer science. And another one had done very good work in computer science, but wanted to do work in pure math. So I gave each of them a problem over the summer to work out in the field where they wanted to work. And they basically didn't do so well. I said, go back to where you started. And Yang, who had started in pure math, continued in pure math. And Mark Nitzberg, who had started in computer science, continued in computer science work. Yeah. I mean, so that's one big difference in having students I mean, computer vision is a funny sort of field. It involves a lot of computer science, but it also involves, a lot of it is influenced by neuroscience, and it certainly involves a great deal of statistics and a certain amount of applied math. So because often the kind of statistics is sort of the more experimental, more exploratory statistics rather than tried and true p-value type statistics. Yeah, so it was a very different sort of field, and the conferences were different. I found I never really got along that well with the engineering community. The real problem I have with engineers is they want to build something right now, and if they don't have something that does something interesting and startling right now, they go on and find another advisor. So, and my very best student in vision, his name is Zhu Songchun. So he worked on these algorithms, which I felt were extremely interesting and fruitful and important. But he would have to do computer runs that took 3 or 4 days to get any results out. And so the engineers sort of shrugged and said, well, that's just some junk that we can't wait 3 or 4 days to get an answer, and totally ignored what he'd done. So, yeah. So you can see there are huge differences. Every field has its culture, and these cultures are all different from each other in interesting ways. I mean, in neuroscience, I had more trouble because again, my big thing there was that I speculated about what are called feedback pathways in a theory which at the time was quite unorthodox. Now it's become more orthodox, but they completely ignored my papers because of that, which didn't bother me, but it was anyway. It's really true. Culture, each field has its cultures, and that it's really important if you do switch fields to try to learn the culture of the field you're entering. I mean, physics has 2 cultures really right now. It's split totally, right? String theory is one culture, and the experimentalists are a second culture, and they don't really talk to each other much. Okay.
Yeah, thanks. One short question. When you established geometric invariant theory, how and why you choose the adjective stable?
Oh, yeah. So, well, it was because I was working very much on this issue of the finite number of points on the projective line. This was the paradigm example that that I started with, and the point was when half of them were all over gathered together into one point, then it seemed to be unstable. It was like a seesaw, and they were tipping the projective line in that direction. And similarly with vector bundles, when you had that big subbundle, which had too big a Chern class compared to what it should have, compared to, I guess it's called the slope of the subbundle was greater than the slope of the full bundle. It sort of destabilized the thing. And there was a thing that was, so I thought, there is something there which is a destabilizing influence. That was kind of the motivation. So I don't know, maybe it wasn't the best choice, but at least I didn't have Andre Vey telling me it was ridiculous the way he said that Grotnick's choice of the French word étal was ridiculous.
Okay, thank you.
Okay.
And another question is from Brian Huang from Kernel. What do you view as a great challenge in science now, today?
Oh my God. CRISPR. You all know what that is? It's an acronym, CRISPR. I don't know actually what it's short for, but it's this molecule that they have isolated, and I mean, you know, a human cell doesn't just have DNA and proteins. The DNA synthesizes a raft of enzymes for special purposes, and some of those enzymes are there to correct the mistakes in the DNA. Others split DNA or untangle it if it gets tangled. So anyway, CRISPR is one of those enzymes, and what it does is it creeps along the DNA sequence until it finds something it's been programmed to look for. And at that point, it can replace a single base pair with a different base pair. So essentially, it is the tool for genetic engineering. Now, at the moment, it's still in early days, and it's a relatively restricted purpose. And of course, most of the research is to try to repair genes where people have one bad gene which is causing a disease. But I think without a doubt, developing CRISPR, and of course you also then have to develop a better understanding of how the genes themselves produce the living creature. But sooner or later, it's going to allow us to tailor make people, other human beings, which you dial up and you say, I wanted this and that. I want blonde, 6'6", you know, whatever you want. So I think without a doubt in my mind, this is the cutting edge of science and the most dangerous, and that it will. This shows nothing whatsoever that will stop it. That's my gloomy answer.
Perfect, thank you. And another question that your foundational theories in algebraic geometry developed a lot and inspired a lot of other research in other areas. And did you expect it?
My foundational work?
Yeah, you just your foundational theories, which you created long time ago.
No, but I didn't have. Well, wait a minute. It was Groening that created foundational theories. I was simply a worker in the area of moduli. I mean, I don't know. Did I create new foundations?
Maybe this is a good answer.
But you know, I mean, what to me is one of the most wonderful things in the world is that János came along and he showed that geometric invariant theory wasn't necessary. It turns out if you understand higher dimensional birational geometry well enough, you can construct moduli spaces easier way. I don't know. I mean, it's kind of wonderful to realize that. I mean, it was fun, certainly. You know, quotients are a powerful tool and all. And I thought theta functions should have been a powerful tool, but that didn't pan out so much. Yeah, but anyway, so it's no, I mean, to me, in algebraic geometry, the unbelievable progress in higher dimensional geometry, birational geometry, is just breathtaking. And of course, I remember first when I heard Mora's result, it was on rational curves, I guess, an existence of rational curves, which he got from going into characteristic P and back. But anyway, you see how vague my memory is. But yeah, so I mean, that was a brave new world. But you know, you have challenges. Codimension 2. What subvarieties are in projective space of codimension 2? Give me a handful of them. Besides complete intersections or the like. Yeah. Yeah, lots of open questions too. Well, the Hodge conjecture, of course, but yeah.
Another question,
Yeah.
a bit predictable. Did you experience an algebraic geometry helped you in a breakthrough in computer vision?
No. That's very simple. No, completely. The math is completely different. There's no, I mean, for me, the real mathematical revelation was the understanding the power of Bayesian statistics. And in fact, I don't know how many of you, I don't, is by any chance Ulf person on this call?
How many? More than 200. Can you repeat, David, please? Sorry.
Ulf Persson.
The Swedish mathematician, algebraic geometer, Ulf Persson, P-E-R-S-S-O-N, Ulf Persson.
If he was
I guess
on,
he's
he would have
not
identified.
on the. It what? And anyway, he published a spoof that I wrote about Bayesian statistics, in which I attempted to prove the existence of God using Bayesian statistics and the stars in the constellation Orion. And he published this paper in the newsletter of the Swedish Math Society. But if you're interested in it, you can find it on my website. It's there under other or something like that. But yeah, so I mean, so statistics. That to me was the most powerful tool, and the work of Grenander, another Swede, who was my colleague. I think I neglected to say that one of the huge motivations for the work in shape theory has been computer modeling of the human body for medical purposes. So it was Grenander who proposed that we should construct a universal atlas of the human body, the typical human body, together with the standard variations idea of, so that we can then isolate what's an abnormal variation. So this would be a model which would include, not down to the cellular level, but include all the organs, certainly the nerves and the muscles and the bones. But the most work has been done in that, actually on the brain, on the hippocampus, where the shape of the hippocampus changes if you have Alzheimer's disease, done by a colleague of mine, Michael Miller, particularly. Yeah, so enough. So maybe only one or two more questions, or maybe that's plenty.
Okay, just maybe one more question, that if you have to give advice to early career researcher, what would that be?
Oh my gosh. I don't know. The world is changing extremely fast. And, you know, I think that my lifetime was a period which was a kind of an intellectual paradise. I mean, forged by what I might call Pax Americana, and involving everyone in mathematics from every country almost. And I don't know. I'm nervous that the world is so big now, and it's so hard to have a big overview of what's going on in mathematics. It's I mean, I personally find infinity categories. I spent some time looking at them, and I really couldn't exactly see the point. Category theory has gone bananas, being wedded to algebraic topology. And anyway, so I don't know. No, I don't have any advice. Just good luck. And if you fall in love with something, let yourself go. Let yourself find your own secret garden, like the one Oscar had. Anyway.
This is a good advice.
Okay.
Yeah, and David, maybe a last question from Ernesto Lupercio from Mexico. What does remain from algebraic geometry in you?
What remains?
Yeah, what
you know, these words are there, you know, you say, you know, a double solid, and I guess I know what that is, but yeah, there's some words, but you know, I wrote that paper in the notices. I mean, being involved in the history of math, I really wanted to understand Enriquez better, and this was a really kind of a love letter to Enriquez, to tell him that I really think I understand why he had a proof of the completeness of the characteristic linear series of what he called a complete continuum. In other words, the fact that that a Picard variety is reduced in characteristic zero. You know, so I had to dredge up a lot of algebraic geometry to write that, but I thought that was my swan song to an appreciation to Federico. Isn't that his name?
Yeah.
Yeah.
Okay.
Okay.
Thank you very much.
Okay. Well, anyway, I'm kind of hungry for lunch now. It's 10 minutes to 1, so I hope it hasn't been too scattered. And I apologize. I thought that I had it all worked out. What went wrong? I still have no idea, and I'm sorry.
It's all perfect. Thank you very much. It was a great pleasure. Yeah. And if you go to Moscow next year, see you in Moscow. Yeah.
Yeah, exactly. No, I hope to do that, and I hope it will. But I don't know when exactly it'll work out. I mean, I look at the stats every morning, and Brazil and Russia and India are all struggling mightily. Okay, good luck. And
good luck. Thank you very much.
Thank you. Yeah, you're very welcome. Okay, right.